Hello, everyone. My name is Josh McBee. Yes, I'm a technical marketing engineer with the IES division within the Digital Industry Software Group of Siemens. And what I'll be focusing on today is a product called that we have called Capital, that is really for electrical system development, but also embedded software development, and then harness engineering, harness manufacturing, as well as smart documentation and those types of things. I'm going to be talking about a particular flow, is what we call it, or really a process around how to design electrical systems in the context of aerospace and what we call the platform interactive flow. So, one of the themes of really today's presentation is going to be around the extreme and increasing electrical complexity that we have within aircraft nowadays, and also just how that is exponentially growing because it's being more and more difficult to manage all of the data that we have to consume from these different tools and systems that all have to come together. And, electrical and mechanical have to be very tightly integrated in order for these aircraft to come together and work and also to meet regulatory compliance. So that's going to be really the theme as you see today throughout these demos, and how with our tool Capital, we'll be able to manage that complexity and break down some of the silos that exist between these different domains. In particular, what you're going to see today is how the complexity that we have within the aerospace industry and with these aircraft, how we can manage that in just the volume of the devices and the amount of wiring that we have. We're going to go through and actually see how we can bring in designs and make sure that we don't have to do a bunch of rework, so that engineers are going to be more efficient in their designs. We're going to understand all the different configurations that we have within aircraft, and be able to manage those, whether it be a UAV, commercial jet, helicopter, whatever it is. We're going to see how we can manage that complexity in those different builds that we have, and very easily change between those if we need to, with different type of configurations. And then lastly, one of the things that always comes up, and especially nowadays, is just the regulatory compliance. Engineers have, tens, 100 kilometers of wire within these aircraft. They have tons of components that they have to look after. They have to, meet the electrical specifications, of all those wires, make sure everything, the derating and everything, the voltage drop, everything has been met. And then on top of that, you have to make sure that you're routing your wires correctly through the aircraft. You have to follow EWIS constraints. All of these things and the increasing complexity makes it very hard for engineers to be efficient at their jobs, and also to make sure that they're doing things correctly and quality, their first time through. And this was just a quote that we had from one of an engineers at one of our commercial aircraft customers, and it just says, with the increase in electrical systems content and iteration in design, verification and compliance validation is so large, it can put a whole organization at risk, and this is why we must change. So how can we help engineers reduce the amount of complexity that they're dealing with? Still be able to iterate on their designs, improve the first time quality designs, and also design, more efficiently, and be able to, validate and verify that their designs actually work without halting a program or, really increasing the costs immensely. That's a very difficult task to take on. And so, we talk about at Siemens here, we really talk about and believe in the concept of the digital twin, and what we're doing by bringing in all this different software and design software together is that you can get a complete idea and validate, you know, everything that you need to improve the first time quality of your designs before they ever go off to manufacturing, and you have to wait for late design changes and issues to come back that will really affect the bottom line, or maybe halt or upend a program altogether. We really believe that bringing and breaking down these silos with this software and bringing a complete model to the customer and bringing that digital twin is what's going to really help in the long run of reducing the overall complexity and first time quality and reducing those program costs. So how can we realize the digital twin now? How can we do that? How can we break down these silos, these natural silos that exist between these design domains like the electrical and mechanical domain? I'm going to really be focusing on those today, because that's what these demos are really going to show, is how we can do that with I'm just going to be showing Capital today, but this is also done with the Siemens NX MCAD software as well that we're bringing the data from. When you look at aircraft, it's very difficult, to really understand from an electrical design engineer's point of view, how the wiring is fitting into the context of an aircraft. We know whether that might be a commercial jet, a helicopter, UAV, whatever it is. It's very important to understand the context that you're designing in. And that's very difficult to do because, you don't have that whole picture of what you're doing and just in, wires going from device 1 to device 2. And then so when changes need to be made, communicating those changes is really done at a person-to-person level. It's through email, it's through word of mouth, it's through meetings, it's through printouts. And, the problem is that the changes that are being communicated, people have to go back and manually do those changes and understand. They have to understand really what needs to be changed. And they also have to communicate in another, interface in another domain, effectively, to make sure that the mechanical or electrical engineer actually, makes the proper change. And so without that digital interface, without that data that's actually driving the change from one domain to the other, it's very difficult to make sure that everything is being updated correctly and that everything is being validated. So what we're really going to see today is that a topology that you have of an aircraft is really going to offer an interface. It's really going to break down the domains between, the electrical and mechanical engineers, because we have an interface for them to actually communicate that's a data source. So electrical engineers will actually be able to, design within the context of the mechanical interface. And so it's really almost like a control document between the two domains. They almost have a contract, if you will, saying from the mechanical engineer's point of view, this is what we have so far. This is the actual data source. This is the source of truth. And then electrical engineers can synchronize their wiring designs and immediately see if there's something that's not going to work. If there's errors, they can validate, they can run design rule checks. So they can immediately see what needs to be changed. And then instead of going back and emailing those changes, they can, send back the mechanical engineer the proper information, because they know they have the context of the mechanical interface that they're designing in with their electrical solution. They can send them back the proper information so that the mechanical engineer can now update his design to properly reflect that. And it's not just through word of mouth, it's through actual data exchange that you might have between these different solutions. And that's really important, because what that's going to do is it means that there's less manual mistakes. Through these word of mouth communications, through these meetings. It's very hard to understand when you're looking at a 3D model from an electrical engineer's point of view. You have to either understand how to read that 3D model or how to navigate it, which is not always that easy. From a mechanical engineer's point of view, that's very easy, but from an electrical engineer's point of view, you might not know what inline you're looking at, or where that's supposed to be routed, or what bulkhead that's going through, or whether or not that particular part is correct that that mechanical engineer has. So interfacing with the different data sources is very important, and it's really important because you really want to have less reliance on manual changes throughout the design to improve that first time quality, so that the data is the source of truth as you're going through your designs, not necessarily what people are saying, and hopefully that they are interpreting what you're telling them correctly. So now, what I'm going to go through is actually show you how we can achieve some of those benefits that we were just talking about with an electromechanical design flow that is really data driven, and it's coming from the source of truth. And we're going to get more into the demo portion where we're going to see how this topology aided flow that we call the platform interactive flow is really going to help us achieve that and improve first time quality and reduce overall program risks that we have. So what Capital really is Capital. A lot of people know it as an electrical design tool, but it's much more than that. It's much more than just electrical wiring and harness engineering. It's really a tool suite that starts at the system model level, that can capture functions and requirements and drive those down into different implementations, either into software and network development, or into electrical system and harness development, which is what a lot of people know us for, as our core set of tools. On that is a data and core applications layer that helps to manage all the data and assets that are in these different tools that we have, and also helps to integrate us with the outside world, with the PLM software, the ALM, MCAD, all those different external interfaces that we need to be able to integrate with, so that we can actually achieve this digital twin and realize the benefits and break down those silos that we were talking about earlier. So I've talked. I know I've mentioned early on just that Capital has different. We call them flows. Different design processes is really another way to think of it. And I just want to go through and briefly explain some of the differences between those different Capital flows or design processes, so that everyone understands what I'm talking about when I say the words platform interactive, because that's really what we're going to be focusing on for the rest of this presentation. The first flow is probably the most, normal flow, what everyone is really used to, especially for an electrical engineering perspective, because it's more of what you think of when you think of schematics, or just point to point wiring. It's really the interactive flow from device A to device B, your connectivity through inlines, through connectors, but you don't really have any other this interactive flow still has tons of automation, tons of functionality, design rule checks, analysis, and all of that, but where it's lacking is really that it doesn't necessarily have the integration into the context of a platform that you might need, like an aircraft, an automobile, so that you can have a better understanding of how all your designs come together and how they actually might be routed and look, so that you can catch errors earlier on before you send them off into the next abstraction for the harness engineering and the form boards and everything. And that's really what the platform interactive flow is. It's bringing in that topology from the MCAD side, allowing, aiding in those system wiring designs, so you can synchronize those things. You can catch those errors earlier on in the design process. You can see the pathways that your wiring can or is taking, and then determine if from that maybe you need to route those wires in a different bundle, or across a different section of the aircraft because they no longer meet EWIS requirements, or EMI category separation and those types of things. And so that's really the difference between the interactive and platform interactive flows. You're just bringing in that topology aid to help engineers visualize and see errors and communicate more effectively with those mechanical design engineers as well. We have two other flows I'm not going to talk about today. These are really out there for a lot of times auto manufacturers will use these because these really aid in assisting a large number of designs with thousands of combinations of options that you might have on particular platforms. It's really a rule-based approach to design where you're trying to capture the IP that your engineers have and then allow the software to actually apply that IP to generate the wiring design. So you're not actually, so your engineers aren't going through and, generating the wiring designs themselves and, the connectors and everything. You're allowing the software to do that for you. And the reason that we have a first pass generative and a generative flow is because first pass generative is really figuring out, okay, there's a certain level of trust that's needed with the software, and make sure that you're capturing your IP correctly, so those rules are being applied, and so that you can specify things like how your minimum splice distance that you want from a connector, the sizing of wires, the naming. I mean, the routing paths that they might take, and in order for engineers to trust that the wiring designs that the software is spitting out correctly, there's iterative processes there as well to make sure that those rules that have been written are correct and that the wiring designs themselves are correct because of that. So that's why there's those two flows, first pass generative and generative. And those are really more, the reason that we don't always highlight those flows is because those are really flows for customers that are facing an immense amount of complexity with options and different platforms and have to make changes that could affect, multiple harnesses, thousands of designs, different types of options. They need to be able to, do. It's a much more complex process to manage all those different variations that you have within some of those platforms. So what I'm going to be going into now is our first demo. And this is just going to be a short video that's really just going to go through it's really going to be like the introduction kind of to the topology and show off a little bit of our automation while at the same time show our platform interactive flow from a system schematic design that we'll have. So you'll see a flight instrument design, and we're going to push that down into the system wiring abstraction. We're going to use some advanced automation to do nets to wires automatically, and then the generation of harness connectors based on the footprints of devices that we have. We're also going to quickly establish correctly through the designs and through the footprints that are associated to our library parts. We're going to quickly establish modular connectors in the correct hierarchy with no issues on that are shared across multiple designs already. The final step that we're going to do, and we're not going to show a lot within this demo video here, but we're going to synchronize that to our UAV topology that we have within capital topology here. And from there, then we're going to build on that to show some more advanced functionality that you can get out of having that aircraft topology. So in this demo, what you're going to be seeing is first going to show you that we're going to be taking a schematic design that we've created, and we're going to be bringing it into existing designs that we already have within our aircraft. And so we need to drive this schematic down into our system wiring. In this particular example, we are doing flight instrument schematics that we're pushing down into our wiring. And so we are using shared devices across our schematics. And so we need to make sure that when we're going from one design abstraction to the next, that we have a correct by construction design, that we don't need to remap all of our devices and make sure that everything is shared correctly once we've brought in this flight instrument design into our system wiring. So what you're seeing here is we're actually mapping, we're using a technique called copy advanced within this, within Capital here. And the reason that we're doing that is, just like I was saying, it's going to bring over those shared components, the connectors, the devices, and everything correctly so that they're correctly mapped to the existing shared devices that we have within our other system wiring designs. That leaves less work for the engineers, allows them to be more efficient because they know that everything's correct by construction when it's brought over. Now, when we first open our new system wiring design, it's going to look exactly like the schematics. But what we're going to go ahead and do is use some of the automation that really helps make our designing more efficient so that we don't have to go do a bunch of manual work. We're going to go ahead and convert all of these nets that we have into wires. So we have a bunch of multi-cores that we've specified within our schematics. With simple automation and with build lists for, to manage and configure different builds that we want, it's simple to do that with just the click of a button with our nets to wires automation. And so now it's already been done and everything's been mapped over. And we now have nets to wires for our entire flight instrument diagram, so we have all our wires in. And then the next step of automation that's very simple, with our footprints that we've defined on our devices, we can simply generate the harness side connectors. Now what we can even do is, let's say we have modular connectors within our designs. I know that's more and more prevalent within the aerospace industry nowadays. It's very simple to go ahead and map modular connectors directly on to existing footprints that we have within our designs. And we can even do that across shared modular connectors within our designs. So for example, one of our devices here has a shared modular connector that we brought in. It's already shared onto an existing design that in the system wiring, but it's so simple. All we have to do is just add that shared plug directly onto that device, and it will automatically correctly establish the parent hierarchy that we have. In this case, there are two children on this particular modular connector. And that's very easy to see here. As we go over to the design pane, I'm going to go ahead and just quickly show this modular connector and its hierarchy. So when we select this A1P1, the parent, you can see the highlight there that shows the entire modular connector as it exists in this particular system wiring design. But then we can also see the pins, we can see the second level child there, and then we can see the first level child as well. And then from there, we can also see, the simple face views and those types of things that we have with our modular connector. The last thing that we can do, and this will really become more important as we go into the other demos, but we're going to go ahead and synchronize all of our system wiring that we have that's been driven down from our schematics into an aircraft topology that has had the MCAD data from NX brought in, so it's actually represented within this UAV that you see here. And this is actual MCAD data. And now we're actually able to immediately show all of our synchronized wiring data that has been brought over. So what we saw in that last video was just an example of, the kind of automation that Capital really can bring, and how it can smoothly transition and make it easy for the engineers to go from one design abstraction to the next. And then also allow them to leverage tools like Capital Topology, where you can see your physical wiring within the context of the aircraft platform, and this really reduced the amount of manual, rework, because you're breaking down that mechanical and electrical silo that we were talking about earlier. And we're going to delve more into that as we get into our next design. But it's really making the engineer's job more efficient through the automation that we have. And then, as we'll see further on, really improving the first time quality as well. So, like I was saying, what we're going to be seeing more is a particular use case for what you might do with the topology aided design that you have within this platform interactive flow of capital. What we're going to be seeing here is the last step that we did within the demo that we just saw was we synchronized the physical wiring to that aircraft topology, our actual MCAD data that we brought in from NX. We're going to use that system wiring now that was driven from those schematic designs, and now we're going to use that to reconcile how the wiring is actually routed throughout the aircraft with those inline connectors that they may have to be routed through. In this particular case, what you're going to see is devices A2 and A3. We're going to have to route our wires through some bulkheads and through particular inlines, and we're going to have to figure out what are the paths that we need to take. What wires are still unrouted, what inlines are available, and if they have available space within those inlines as well, and also do they have the correct cavities that we can actually terminate those wires into. So let's go ahead and we can get into that demo now. So in this demo, we're going to start off in the topology plane here that you can see with our UAV aircraft that we have here, where we've already brought in this MCAD data. And from our last demo that we did, right at the end of that demo, what we did was we synchronized all of our wiring data to this particular aircraft topology and this MCAD data that we have. Now, what we can quickly do is we can go and see all of this, all of these wires that we have that we brought over, and we can go see those physical sources as we just did in one of those wiring designs. What we can also see is with the routing assistant and the automation that's built into Capital, we can see the path that this wire has to take. But one of the issues that you have is what you're seeing on that left-hand side is all the unrouted wires that we have within the aircraft. All of those, what we have below is in the window below is the routing assistant that's telling us, well, these wires actually have to travel through two bulkheads and two inline connectors in order to get from device A2 to device A3. With Capital and with this routing assistant automation that we have, we can quickly go and see the best paths that these wires have to take in order to get there. And we don't have to do this one wire at a time. We can do this for all the wires that are going through a particular inline and figure out exactly how they need to be routed and what's the best way to do that. In this example, we're going to route two sets of 4 wires going from device A2 to device A3. And what you saw there is we actually told the software right there that we would like for those wires to run through this particular inline because we had multiple choices that it could run through there, and it automatically places that inline back into our system wiring designs. And we know that that's the correct path because we've seen it in the context of the aircraft topology. Now from there, we don't even have to go back into the topology plane. We're still within the routing assistant, and we can see that there's another inline that those wires have to take in order to complete their route. So this 981J2 and P2 connector here, this inline connector, we can also run the routing assistant on that to see which wires we need to route through that in order to complete this connectivity for between these two devices. We can also run inline connector reports to make sure that we have enough space within these inline connectors so that we can actually route the wires through there, make sure that it's the correct cavity size that we have for those inline connectors. And if we don't, then we can figure out if we need to change the particular inlines that we have, talk with our mechanical engineers, or maybe add more bulkheads if needed. It's very simple with the routing assistant. We can now again place that. We can see within our view there. We can see the different connections and where they've terminated through those inline connectors. But now we've established all our connectivity for those particular wires. So those are no longer unrouted because with the aid of the aircraft topology that we have, we're able to quickly visualize where those routes need to be and also finish those routes with the routing assistant and the automation built into Capital. Here what I'm doing is I'm actually finishing off all the routing of all the wires within the topology. So we have 12 wires left, and I'm simply placing those and placing the last inlines that we need so that we no longer have unrouted wires from our system wiring that we brought in and synchronized to this mechanical data. So it's nice with this because now you have the context of your MCAD data, and it makes it very simple. You know that this is correct by construction and is also synchronized across the electrical and mechanical domains. And so it makes it very easy if there needs to be changes or if we need to update something or if something doesn't fit, it's much easier to see what changes need to be made and how we can communicate that across domains. And that's what's really nice about having the context of that mechanical system in the electrical tool. So what we really saw in that demonstration was the power of bringing those ECAD and MCAD domains together, allowing the electrical engineer to design within the context of the mechanical domain, but in the context that an electrical engineer can actually understand instead of looking at a 3D model, that 2D interface really enables them to better understand, the wiring and how the physical wiring and the implementation actually looks within that aircraft topology that they need to be working with and that they need to communicate with the mechanical engineer to ensure that those designs are correct and that they are using the correct inlines, that they're going through the right bulkheads, that they're ensuring that they're taking the right routes, that the cavities that they're using are the correct size to terminate those wires in. Everything that could come up later on, whether it be in the harness engineering or worse in the manufacturing stages, can be caught early on because you're enabling the engineers to actually find those errors and then communicate those errors using the data source. So it's improving, overall first-time quality, reducing your program risk, and then also increasing that design efficiency by allowing, that automation with things like that, that routing assistant to easily be able to identify where those paths need to be taken, placing those inlines, and then also back annotating that information directly from that MCAD data into your physical wiring designs before we push that off even into the harness. So there's going to be one more demonstration video that will be a short video, and what this is really going to show here is some new and advanced functionality that we have within Capital, particularly for Capital topology, and what we can do now that we have that context of the platform in the electrical engineer's hands with Capital topology and the use of that MCAD data from an X. We're actually going to use the integrated 3D viewer that's available within Capital to view that Capital topology and show that we can actually cross-probe between our design and the 3D view that we have of the particular harnesses. Now, what's really interesting about this 3D view is it doesn't bring in all of, the clutter and the noise from the mechanical model. It's just what's relevant to the electrical system designer for the physical wiring in this particular case, the bundles that they want to route through the inlines and those things. Next, what we're going to do is we're going to import a signal separation data file where we're just going to simply specify the distances that we would like to see between the minimum distances that we would like to see between different EMI categories. And then lastly, we will use a built-in design rule check to ensure that those spacing requirements are met. So let's go ahead and get into that demo. So in this demo, what we're going to be seeing is first, we're going to see the context of the aircraft in a 3D view. And while I've been talking a lot about just this platform interactive flow and how we can do so much just bringing in the MCAD data into this 2D view, the 3D viewer is nice in certain situations where you might be doing things like, say, signal separation, where you actually can't see that other plane, and to determine, whether or not there's enough distance between particular harnesses and bundles to make sure that those signals are separated the minimum required distance. You can also bring in CSV files to set that minimum separation distance between those different EMI categories with that set separation there. And then there's now a built-in DRC warning that checks for wiring that's breaking those separation rules. You can see it's under the consistency tab there of our design rule checks. And so when we go ahead and run that, what you can see is there's a number of wires that are throwing errors, but you can see the common one is this W1 that consistently is throwing an error, and we see it's routed along the same pathway as these other wires. You see that W1 is coming off of that TB device there, and it looks like it has another routing path available to it within that harness. Going through this 681 LP2 inline connector there. So what we can quickly do is we can navigate to where that wire is to see where it's going right now. And if it's going through an inline and being routed through a path that we don't want, we can quickly delete that. And then we can go through the same exercise that we did within the last demonstration, and we can actually we can actually use the routing assistant within Capital to quickly see what other paths are available and if there's better paths available for this. So we've gone and updated it so it's no longer going through that other pathway through that other inline. We can quickly route it through this 681 inline here. We can see that it's still not quite finished after we've synchronized the wiring back in topology, and that we still need to go through this 981J3, and then once we've done that and placed our final inline, we can go ahead and rerun our design rule check to make sure that we've satisfied all of our EMI categories. So this is really just showing another way where, with the context of the aircraft topology at the electrical engineer's disposal, you can now take into account EMI separation requirements as well. So in that demo, we were able to see how we could use the synchronization of the physical wiring and the aircraft topology to ensure that our designs are validated against our signal separation requirements, our EMI category requirements, and also just the ability to also use, I talked a lot about how, in the context of the 2D view that you have, bringing down and simplifying that mechanical data set really benefits the engineer because then they don't have all that noise. but that 3D view is sometimes necessary, especially when it comes to signal separation, because you need that Z-plane in order to ensure that there's enough separation between the bundles and the wires that are running through those bundles and everything. So that's what that demonstration really showed, was just how, again, this can help with the validation process and really help engineers be, you know, meet their regulatory requirements as they're going through their design, which is so important nowadays. And capital is, you know, we've been serving the aerospace industry for quite some time now, and we've had a lot of great success with our customers. Here's just some, data points that we've gotten from, feedback from various customers who have deployed capital. And so if you're looking for a software suite that can bring, you know, the necessary changes and enable your design process so that your first time quality is improved, so that your engineers are more efficient in their design, so that you can reduce your overall program risk. This is really the software suite that can do that for your electrical system design. And then also just break down those barriers so that you're starting to have one single source of truth, which is that data source, instead of word of mouth. So you can really eliminate most of those manual errors. As you can see, a lot has been done just from customers already in some of those areas. So I just want to thank everyone for attending today. I hope you enjoyed it, and I hope it was relevant. So thank you.